Okay, this is Bioengineering 599J. I think this is week number 5. Okay. And every quarter, I try to set aside one seminar for student presentation. And today is that student presentation day. And as Todd McDevitt mentioned last September, when you get a call from me about finding out whether you are willing to make a presentation, what that means is you are expected to graduate, or otherwise you'll be kicked out type. So I recruited 2 outstanding senior PhD students. What that means is that they are almost ready to defend their dissertation, and probably applying some pressure to advisors as well. And today we have first speaker is Melissa Lambeth, and she got her BS degree in nuclear engineering at MIT with a minor in biomedical engineering, and she came to UW in 1997. And she has been focusing on computational bioengineering track under Professor Marty Kuchmarek, and she'll be giving us a presentation with the title of Exploring Regulatory Properties of Skeletal Muscle Glycogenolysis. Okay.
Thank you, Dr. Kim. The talk I'm going to be giving today is, as Dr. Kim said, I'm in the Computational Bio Engineering track, which is usually a little bit more underrepresented in the student body of the graduate students. So all of you first-year students, if you're interested in computational bioengineering, this is one example of something you can do within that track. So the project motivation, I'm going to list several goals that I originally had for this project, and I think like all PhD dissertations, there's some anecdote about how the project evolves with twists and turns along the way. And in my case, we kind of joke now because as my first summer in Marty Kuchmarek's lab, I suggested making up a kinetic model of glycogenolysis, which is the pathway from glycogen to lactate in skeletal muscle. And Marty thought that was a great idea for me to sort of jump into the lab and get started on a small project before I figured out what I wanted to do my dissertation on. And of course, it developed into a many-year endeavor. So the original goal was to just take the existing information in the literature. Over the last 5 decades, enzymologists have been collecting kinetic parameters on all these glycolytic enzymes, and we thought it'd be really nice to take that information and assimilate it all together in some comprehensive, cohesive, quantitative description. So that was the original goal, was to take this information, put it all together, and see if we can explain what actually occurs in mammalian systems. So once we had the model in place, we thought it'd be very straightforward to explore which interactions are important in the system and test for competing theories of regulation. And eventually, the ideal would be that this model would be so rock solid that we could then use it to predict behavior in human skeletal muscle and develop new experiments from the model. And as you listen to my talk today, you'll see where I am in all those goals. So an overview of the biology. Kevin Conley's group in the Department of Radiology and Physiology has done a lot of work on understanding the system of skeletal muscle metabolism. And one thing that's interesting about glycolysis and glycogenolysis in skeletal muscle is that models have been developed in other cell types, but skeletal muscle is really unique in that the flux can span from a very, very small level to a 100-fold greater flux when you're maximally exercising. And so the regulation is a little bit different than other cell types where the enzyme activities correspond pretty much to the flux rates. So there's sort of different ideas about how all this is regulated, how the flux turns on and slows down again. One idea is that you have metabolites that elevate when ATP hydrolysis occurs, and these metabolites then activate the system. The problem with this idea is, while it's partially true, you can see high metabolite levels when the flux is turned off. So the mass action effects alone on the system are not enough to drive the system forward. And Greg Crowther, who just graduated last year in the physiology department, wrote a series of papers about the turning on and off using some of these ideas. Another idea is that calcium is what activates the whole system. And calcium, of course, Ed Krebs here at University of Washington won the Nobel Prize for showing how glycogen phosphorylase is phosphorylated and activated by phosphorylase kinase. And that is a calcium-induced phosphorylation event. However, we also know that the phosphorylase reverts from the active A form to the inactive B form while still at high contractile activity. So again, it doesn't seem like just phosphorylation can account for the flux behavior either. Now, what I'm going to be talking about today is not the oxidative phosphorylation box that you saw in there. We're talking about the pathway of glycogenolysis just in isolation. So in a physiological system, you can think of this as in the absence of oxygen, you'll just have anaerobic activity, and glycolysis and glycogenolysis will supply the majority of your ATP for the ATP demand. You'll have creatine kinase, and that's included in our model, which buffers the ATP. And in the case of the basal experiments I'm going to talk about today, we're going to assume that calcium isn't present either. So for the model description, I linked together a series of differential equations using enzyme kinetics and just simple known effectors. We didn't. The kinetics of each enzyme have been studied under numerous different activators and inhibitors, and we tried to just focus on what was present in the model and what would have feed-forward and feedback effects, and did not try to include the gamut of effectors that have been studied. We define the amount of glycogen phosphorylase A, the active form in the system, and that's a parameter which then, you know, for low basal activity, we can do around 10%, whereas at a very high activity, we may set that towards 40%. But that's also a parameter that can be fitted in the model. We use fully reversible equations, and we're able to do that even though the reverse Vmax is often not measured, as long as we have these other four terms, the Vmax forward, which is often measured, the Michaelis-Menten parameters for the substrate product, and of course the equilibrium constant, then we're able to describe the backward reaction as well. We include near equilibrium reactions, even though they may not be important in the regulation. We include them anyways, and we also include imposed stoichiometric constraints. So the total adenine nucleotide pool in the system is a fixed constant, although the variables are allowed to change. They always have to sum up to the same value. Same with the total creatine, the total redox in the system. And by doing this, we actually come up with some implicit stoichiometric constraints as well, such as the total phosphate in the system remains constant, even though we haven't specifically defined that. So here's a picture of the pathway. Those of you that took basic biochemistry probably remember this. Glycogen goes all the way down to lactate and splits at aldolase. So everything below this are 2 3-carbon molecules for the 1 6-carbon molecule up here. As I mentioned before, we include creatine kinase, the adenylate kinase reaction, and the ATPase in the system. And then we can describe the rate of each enzyme in terms of, this is just a very standard basic enzyme kinetic equation for a reversible Michaelis-Menten enzyme. This is the simplest case, such as enolase right here, where you just have one substrate and one product. In the case of multiple substrates and multiple products, such as one of the kinases, this becomes more complicated, and especially the more information you know, such as phosphofructokinase, which is allosteric, then we have to build in those terms as well. So once we've constructed the model, what we can do is a control analysis at different flux rates. I mentioned before the fluxes vary from very small basal levels to maximal. So we ramped up the ATPase in the system and then looked at how each enzyme, if it's perturbed in the system, affects the overall control. And you can see at basal levels, the control resides in just a few enzymes, whereas at maximal exercise, it becomes distributed, the black bars. It becomes distributed more among multiple enzymes. However, besides this internal shift in the system, what's really important is what I haven't shown, which is the ATPase control in the system, because if I included this on the graph, it would just dominate the overall picture here, because ATPase actually has about 95 or more % control of the pathway. Now, if you look in any biochemistry textbook, you'll see glycolysis and glycogenolysis described as controlled by the PFK, the phosphofructokinase enzyme, and that's a bottleneck which regulates the rate of the flux. So this work, as well as work by other people in metabolic control analysis, shows that often these metabolic systems are controlled by the demand on the energetic demand on the system. In this case, it's the ATPase. Once we did a control analysis on the system, we then expanded the model a little bit to include pH effects. Well, why would we want to make the model even more complicated? First of all, acidosis is a known result of glycolysis, and it's an easily measured variable in NMR in vivo experiments. You can use the chemical shift of the spectra from NMR between the inorganic phosphate and the phosphocreatine, and the distance between those peaks will actually change relative when pH changes. So that's a direct measurement which we can then use to quantify glycolysis. And another reason, which I'm not going into here, but Jim Bassingthwaite and Callion as well are working very hard on trying to link these metabolic models up together, and proton transport from the mitochondria is a point of connection between glycolysis and oxidative phosphorylation. So if we build that in, then eventually that's a coupling point for how those two energetic modules talk to each other. So how did we do this? We tabulated the pKa values for all the metabolite ionic species. We used Henderson-Hasselbalch relations to calculate the fraction of each metabolite and its different ionic charge at any given pH, and then also used algebraic functions for the pH dependence of the activities. So now there's a lot of information on this slide. All this data was collected by David Marcinek, who's a postdoc with Kevin Conley. And what he did is he took some mice, put them in the NMR magnet, and had a coil around their hind limb and occluded the blood flow to the hind limb. So these mice are sitting there for about 20 minutes under ischemic conditions. And then he just watches the phosphocreatine fall over time. And at the end of the experiment, he then rapidly pulls the mouse out, freezes the muscle, and then biochemical analysis can be done on the lactate formation, which is the end product of the pathway. So by this method, he can get phosphocreatine, inorganic phosphate, AMP and ADP and AMP dynamics, as well as the pH that I mentioned before. So now, if you focus on this upper left-hand corner, this is the data that I used to fit the model. I allowed 3 parameters to be varied in the system, and by fitting these 2 variables, the model can then predict the dynamics of these other 4 variables in the system. So we were really excited about this result because it indicates that you can use an in vitro model like we've created and explain some very complicated in vivo data. And muscle is a highly structured cell type with lots of reported enzyme-enzyme and enzyme-actin binding, and people have talked about impaired diffusion and so forth. All these spatial effects seem to have no relevance when you look at an in vivo system, so this is an important result. We can then take the model and do some exciting things like plot pH versus glycolytic proton production rate, and look at some theories about glycolytic regulation. For one, people look at the PFK profile according to pH, and they see that the activity sharply falls off at low pH, and they assume that glycolysis slows down with low pH. This result shows that actually the amount of glycolytic flux continues at low pH, and perhaps if we carried this out further, it would eventually fall off. But this actually goes against what you would expect from just the phosphofructokinase profile. So what I'm doing currently is I'm using the model now to make some predictions about the way muscle regulates glycolysis. One reason we're doing the experiments is to further validate the model, because as I showed you all that data in the other slide, it included nothing about the internal dynamics of some of the metabolites, and we really don't know how those change with time. So one goal was to test the dynamics of less frequently measured intermediates. So I needed to come up with a method to measure some of those metabolites over time. And then we can ask, how is flux regulation affected in known fiber types with disproportionate enzyme concentrations? And we can use what nature gives us in terms of glycolytic and oxidative fiber types. And we know not all of the values are reported, but some of them are. And there's not a constant ratio between the fiber types of the glycolytic enzymes. So the modeling gives us the ability to distinguish between influences of metabolite levels, which are different in these two muscle types, and enzyme activities. So what I'm doing currently is, with the help of Rudy Stupard in our lab, I'm isolating mouse muscles and sticking them in an anoxic 20-degree chamber, which is temperature controlled here with a water bath. We hang them up on a force transducer at an in vivo length. We can poison the mitochondria so that we know there's no oxidative phosphorylation going on, and continue nitrogen gas in the system so that the oxygen is not present, and then rapidly freeze the muscle at different given time points. Then after preparing a muscle extract, I can use ion chromatography to analyze the metabolite concentrations important in the pathway flux. And what I show here is just a chromatogram with two different muscles. The method is sensitive enough to directly compare individual mouse muscles. So we can take a Soleus, an oxidative type muscle, and EDL, which is a glycolytic type muscle from a mouse leg, and do direct comparison within the same mouse of their two muscle types on an individual muscle. And in the past, the way metabolites have been measured, glycolytic metabolites, is generally the enzyme assays used require a very large volume of tissue. And so the neat thing about this anion exchange ion chromatography is that we can do all of it with one shot. And these are just preliminary results, but what I want you to see by this is that the Soleus and the EDL muscle, despite their set points being different here, you'll notice the scales are different, the pattern of the metabolites acts exactly the same. And so now we can ask, once we know that the mass distribution has the same pattern despite differences in the absolute concentrations, we can then ask, what does the model require based on, I'm only showing 3 metabolites, but we can get up to 6 or 7. We can then ask, well, what's required in order for the model to fit this? Do we have to have a constant ratio of enzyme concentrations between the fiber types? Do we have to change the ATPase rate between the different fiber types? So that's something we're currently exploring. So in conclusion, this computational model that I've shown you today allows us to analyze control of the pathway, demonstrate the importance of coupling additional energetic reactions to the model. And this is particularly important for those of you that are interested in modeling. If you want to look at a specific pathway, whether it's metabolic or signal transduction or whatever, it's very important to consider the context of the pathway. In this case, we included creatine kinase and the ATPase in the system, and that proved to be very important in understanding the dynamics of the system. We can shed light on myths of flux regulation by bottlenecks, such as phosphofructokinase. We can now fit and simulate NMR in vivo experiments and develop testable hypotheses of basal anaerobic metabolism. So I'd just like to acknowledge the Kushmerek and Conley labs. I haven't listed everyone here, but my advisors, Marty Kushmerek and Kevin Conley, has been very important in developing some of these ideas. David Marcinek and Rudy Stepard with the data collection. And in bioengineering, the folks at NSR and the Resource for Population Kinetics, both groups have been really important in providing me software for developing the model and insight on how to model these kind of systems. And our funding is from the Whitaker Foundation and NIH.
While David is setting up this presentation, we can take maybe 2 questions. One? Okay, Jim?
Well, a question on the modeling one is that the phosphocreatine, the middle data point of the 3 data points was below in both muscles. Could you comment on what that might mean with respect to the physiological or the modeling?
Well, I wouldn't put too much emphasis on the modeling in that particular graph. That was a first attempt at matching up the experimental results with the you're talking about the ion chromatography. The experimental results with the modeling results. And what we did is we used a mixed fiber type enzyme profile to fit both of those graphs. Whereas in reality, the creatine kinase may be different in the 2 muscles. Perhaps we have a wrong value there, but that's what it would indicate to me, is there's a lot of refinement that needs to go on.
So for the software that you use, is it mostly just equation solver software, or is it actually custom for this kind of work?
No, both software packages are numerical integrators. The SAM2 software at RFPK is actually designed for pharmacokinetics. I just use it for the purpose of integration and optimization, so I'm not using for its original intent. But the JSIM software at NSR has the ability to do partial differential equations, which I'm not doing at all. So they're powerful tools.
Okay. Let's move on to the second presentation by David Craig. David came to UW Bioengineering PhD program in 1998 after receiving his BS degree in both environmental sciences and microbiology from University of Arizona, with a minor in chemistry. And his research at UW has been focused on the computational method to investigate the effect of force on the extracellular matrix protein under the guidance of Professor Viola Vogel. But today he will give a little bit different presentation from his PhD dissertation, and with the title of Research and Entrepreneurship. David.
Thank you, Dr. Kim, and thank you for having me talk. As Dr. Kim said, I'm not going to talk about my research. My research, like Melissa's, is computationally based on fibronectins, modeling proteins, and the molecular dynamics. And so if you have any interest in that topic, I love to talk about it. I'll also hopefully be presenting not too long in my dissertation and also in upcoming conferences as well. So the topic I am going to talk about today is research and entrepreneurship, and this has been something I've really gotten involved with over especially the past 2 years, and specifically addressing questions of how do you supplement our PhD education with something beyond the traditionally what people get. And when you look at the aspects of how you provide and how you create new researchers who will have a career in scientific and engineering disciplines, pretty much you think of you're going to teach them traditionally how to conduct scientific research, how to generate hypotheses, how to interpret data. You're going to teach them how to fund it, because as we all know, funding is the way we have these ideas and we bring them to something and bring them out, because we're all kind of inventors at heart. That's why we're in engineering, and we want to see this basic idea come out and impact people's everyday lives, and to do that takes funding. The last aspect is dissemination, and in academia, that's traditionally, and for us, what we're taught is in publication, presentation, much like today. There are other aspects, points of these three broad concepts that traditionally you don't see taught a lot, but they're still important. And funding of research as it comes from industry. Much of the technologies that impact our daily life are not entirely funded by government researchers, as we all know. Industry plays a large role. But how do you supplement the PhD education? How do you prepare these graduate students to recognize that? Because many of them will, in fact, end up in the industry side of getting funding. The other aspect that affects everyone here, especially the university that's publicly funded, is how do you commercialize this technology? How do you bring things out of the research lab and further into the marketplace? This is a graph, I think, kind of popularized and adapted from Congressman Eller when describing the funding landscape that bringing any new technology faces. And at the beginning, you start with technology, you start up at the blue. I didn't take the pointer, so I'll use a shadow. There's a lot of funding at basic research. This is where we are. The government provides this because it's not favorable for industry to go in and put... There should be pointer. Thanks, Melissa. Put considerable money into it. And so this is where the government steps in. And later on down the road, as technology and research gets further and towards something that may be used by everyday and commonplace applications, and especially in bioengineering, things that affect our health, this is where industry picks up. But there's this gap here that I think it's referred to as the valley of death. And this is where you're taking technology out of this environment, out of academia, into industry. The value really isn't there for industry to pick up and fund it, and government isn't necessarily providing funding for it. And this is an obstacle that we as researchers, especially in academia, face, and I think in a lot of different ideas that people have when they're doing the basic research and have this something down the road they want to get to, something that they have to face. And the reason there isn't funding in this area correlates a lot to kind of the red line in this graph, which is kind of the value of technology, and it really comes down to the value isn't worth it for industry to pick it up at that point. So how do you address this? Because the reason we're here is to bring technology into people's lives and to invent things that's going to affect their livelihood. And how do you teach people this? How do you supplement a PhD education? And how do you teach people how to value what they're doing and how to change this curve, how to change something from going through a valley of death so that it's small enough that it can be surpassed? How can the type of research that's done at the early stage, at the government stage, be thought about and be accomplished such that it is likely that that valley is much more smaller and that industry will pick it up? How do you teach people about intellectual property protection? You have to have a way for industry to take this technology and to capitalize it, because otherwise there really isn't a mechanism just to deliver it out into the marketplace. So in the kind of classical education, a lot of it is done through seminars and classes and clubs and organizations. So the kind of two areas I'm going to talk about. I'm going to talk about this from my own perspective as a graduate student and kind of the experiences I've had along the way. I also hope to provide insight into, for the faculty and, what types of opportunities are being developed that both benefit them while educating the students, because this is kind of the unique thing about the university, combining research and education together, doing some sort of public good by investigating, the interesting topics that we do in bioengineering, but on the other hand, providing the education. I'm going to specifically talk about things that I've been involved with, and I've tried to get involved with quite a few things, the programs, classes, and seminars. And one thing I will say is that these aren't things that you necessarily receive in an email every week. There has to be a certain amount of digging, and so that's part of the reason I'll talk about them and the things I've become aware of. One thing I have participated in is business plan competitions. I'll address that to a certain extent, and I will lastly talk about some of the clubs and organizations. And throughout this, the two areas that I'm going to be hitting are how this supplements in terms of these two italicized points: industry, teaching and how to get funding in industry, and teaching and how to get funding, how to disseminate research through technology commercialization. Now, seminars, this is an example of a seminar, and this is an example of the education process that we all get. This is what I think when I think of education and the PhD. I go to numerous seminars because they don't take much time. You can get a broad overview, and you can get the opinions, the anecdotal stories from leaders in the field. And because this is familiar to most of us, I won't go in a lot of depth, but in the University of Washington, the past couple of years, there's been, a lot of new people been hired. The Office of Technology Transfers changed. In the medical school, there was recently, Susan Ray was hired, and I wanted to point out that beyond the seminars that are in our department, some of the other departments have really created seminar series that affect us. And the first being the medical industry relations. I list there some of their past seminars. I think the last one's an upcoming one, and I think they are relevant to the type of research that we do. How you get new company financing, the University of Washington commercialization process. And the great thing about the internet is you can look and you can find these things, they archive them, and if you miss some of these, I think they're worthwhile going to. The business school also offers things that seminar series that directly impact bioengineering, and they bring in leaders in the field of biotechnology to a certain extent. Corixa was recently in their high-tech speaker series. They brought in a number of venture capital groups, and there is an emphasis, at least in that school, on IT. Moving beyond seminars, the next step in our education as PhD students, and the ones that I received, involves the classes. And the first thing is, when you take a class and you're doing research, I think I talk to friends and family, and they have this kind of expectation that getting my PhD involves taking a lot of classes, and they're surprised at how few classes I take. And I think that's probably because we spend so much time in the lab. And when you take on a class, it is a significant time requirement. If it meets Tuesday and Thursday at 2:30, you can forget about Tuesday, Thursday afternoons. You can forget about your evenings. And so taking classes, you have to be selective. To that extent, there are benefits. You're going to get greater depths, it's obvious. You're going to get documented participation. It's hard when you're talking to someone and trying to convince them that you have an understanding, evaluation of new technology because you went to a seminar in it. A class is something that's a little bit more, you can point to, it means something. Within the engineering school, I haven't seen a lot of different classes in technology commercialization, and I think that makes sense because that's not where our expertise lies. It lies in studying very complicated systems and developing solutions for them. The ones I mentioned there, two that I was involved with: technology-based entrepreneurship, which is partly associated with bioengineering, and I've seen periodic IP classes. What typically you see in these classes is the idea of building a business plan. I think that most classes, this is where they start. And there's an intelligent reason for that, because when you look at that curve that I showed you earlier, the fact of the matter is every one of us will likely be somewhere in that curve. We may be in academia, we may be down the road in industry, but we're dealing with technology and we're trying to bring it one step closer. And the idea of building a business plan is, let's take a look at that whole picture. Let's start with a technology and let's look at what it's going to take to fund it. How are you going to get it there? There are different paths you can take. There are different ways you can market it. You can partner. You can protect this type of IP. There are different focuses. Those are the types of things it forces you to think about that come out of this business plan. And so I think it is worthwhile that they do offer that. And I wouldn't be put off, because one of the things that you see focus on throughout any of the classes at the university is the word entrepreneurship. And I'm going to address that a few more times in the talk, because I think having a clear understanding of what really is meant by entrepreneurship is important to why you should or we should get involved in it. Because I think the traditional definition where people think of starting a new company isn't necessarily accurate towards the benefits. I said the engineering school doesn't offer a lot of classes, and partly because this isn't the expertise. The School of Business has gone into that area. I see Youngman, by the way, laughing. Well, I know he's thinking all the different IP that's been generated. But in terms of expertise, what I'm referring to here is how you value technology and how you educate someone in the process of bringing something on the business side from basic research to the marketplace. And so the partnership has been formed between the business schools, bioengineering, and the other engineering and science schools to create the TEC program. And I know the first years and students have kind of been given an introduction to this, and I'll go into a little bit what this is, because I was one of the first classes, and there has been pretty good participation from engineering students. And the idea here is to have students take MBA classes with MBA students, have them require an application and a series of courses, not just one course. And do something a little bit different, because there's this question that I hear the professors at business school go, how do we teach something we're really not experts in? We're not experts in the industry side of things. We don't know, necessarily how a company values something. We know what we believe. And so to solve that problem, there is the involvement of a lot of mentors from the community. And these are leaders in businesses such as Carixa, such as law firms that deal in IP, and bring them in and teach. And so when you think about the classes that are involved with this, the first, there's a series in the certificate, there's a series of 4 classes that I was involved with to get it. And the first kind of starts out introducing you to the different kind of anecdotal case studies that people, that leaders give, and telling, how I made it. And that's what you kind of expect in the beginning, but what you assume, the later courses, I think, provide something that, as engineers, we really need, and that is finance. If there was one thing that is useful in terms of the courses that I've taken, it's finance. I'm an engineer. I love quantification of things. That's why I didn't go into, straight science. I wanted to obsess about how do you quantify something, and in a way, that's how you quantify technology in terms of evaluation. And just like my computational modeling, it's partly art, partly science, and how different people are going to see, how you value this, and how different people are going to suggest how you fund it. This is something that is going to affect all of us, though, in terms of our jobs, because our research comes from funding. And how do you get this funding? And how do you get it outside of the traditional ways of writing grants? And how would you get it if you were in a large company, if you were in a small company, if you were starting a company? The 2 other courses, actually the one other course here that I was involved with, one of them, Business Models for Emerging Technologies. This is an interesting course. And the reason I mention this is because here's the idea of, let's try to benefit the professors here and the research here. We are trying to give people a real-world education, so bring MBA students, bring research graduate students together and have them work on building commercialization plans for technology developed at UW. Now, the benefit, the reason the professors are interested in getting involvement is, a certain part of grants is showing a commercialization pathway. The other aspect is most people are involved in this because they do want to see their technology materialize into something. You can get more and more involved, and the TEC certificate is one example. It's something that I spent considerable amount of time in. The realistic expectation is for a student they're going to spend 1 or 2 years taking these 4 courses, because within research it's very difficult to take a class, and so you have to consider taking them very carefully, and you don't just take them sequentially necessarily. It might work that way, but I think for many people who've been involved didn't, and so I think part of the people watching this are first-year students and thinking, how am I going to fit all this in? And I'm going to hit that point later on, but know that balance of time is going to be critical. To take it a step further, there's another thing I participated in, and an outspun of the TEC program, which is sponsored by the Business School Center for Technology and Entrepreneurship, is the WRF Capital Gates Fellowship. And this was the idea here, bring together the same type of maybe a smaller group of students and have them spend a summer internship working with 1, 2, or 3 professors developing commercialization plan for research. Have them work in an area, for myself, have them work in an area that they know well, such as nanotechnology, such as, bioengineering, biomaterials, and work with a research group and determine the valuations, funding requirements, financial models, IP, and so forth for this types of research. Specifically, myself, we got involved with professors both with OTL and P&L. OTL is the Office of Technology Transfer, and through them we worked with Kirk Beach and working with his inventions and technology in the area of developing ultrasound for detection of breast cancer. And part of the NCI requirement was showing a commercialization pathway. And we worked with him to develop a business plan for it, to explore different funding options. Another one of the technologies we worked on was through P&L, and this was technologies developed by Drs. Anna Gutowska and Daryl Fisher, and they had developed at Pacific Northwest National Laboratories a type of stimuli-sensitive hydrogel that could encase radiation and be used potentially as a treatment for cancer, as a type of brachytherapy. And the idea with the fellowship was not to focus on the classes, but bring in the community, bring in leaders. For us, it was, learning how to value technology from the CFO of Corixa, where she taught us what she uses to acquire technology, working with venture capitalists, for instance, Ron Howe at the WRF, telling us what requirements he uses to decide whether or not to fund. And when I say telling us, it's really much more than that. It's working with us, working on a day-to-day basis, and working with these people and gaining from their knowledge and getting their perspective, because in the end, those are the people that are somehow going to be involved in our future research, whether it is in industry or in academia, and having an understanding of their perspective is critical. The idea also with this fellowship was to have a continued involvement, and I continued to work with this group throughout, and it was given an interesting idea to us at one point. You know what, you guys are building business plans. Go and try to business plan competitions. And this seemed a little bit odd to me, because I always thought of these as really dot-com things, kind of crazy, 2 people in the back of the, kind of back corner saying, we need a web this and this. And that's one of the things that I was surprised how important it could be towards people's research here, but really isn't. And so we participated in 2 plans. One was a national one in New York, and I think there were about 250 to 256, somewhere in there, proposals sent in, and they were graded, and we actually made it to the finalists. And when I went to the finalists, I looked at the other 8 teams, and the other areas were really interesting. They were all PhD students, coupled together with MBA students, trying to bring forward their research. And these were the ones that were winning. And when I say winning, they were winning $50,000, $100,000, and they were going around the country winning these competitions. Some of the ones that won, the one that won at ours was a portable CAT scan device. Was developed by some a student's PhD research. There were some professors who developed a pap smear replacement, and it teamed up with PhD students and medical students, and they actually won, I think, over $100,000 at the University of Texas competition. And the point is when you hit this valley of death, you have to be pretty inventive in terms of funding it. So things like this, bringing in $100,000, it's a way to bridge technology out of the university, because it's never just a clean, okay, we take the technology, we bring it out, there it is, there's a company that exists. A lot of times it involves an incubation period where part of the research is still going on at the lab and part of it is going on outside of the lab as well. And I think that there are a number of professors who in this department are actually going through this process. I think Jim Bassenwaite, I've seen some of, you have a group also at the WRF, which is one of the organizations I've worked with. And I think that, how you incubate your technology is interesting. And this is something I would point out to people, because I don't think it was straightforward, and I don't think it was something that I thought about in terms of, how to learn something, how to supplement your education, getting a PhD, and on the other side, how to benefit your research by providing funding. We also participated in the UW competition, and we were fortunate enough to win that. With that comes attention to research. Attention to research can be a good thing and a bad thing, and you got to be careful with it. But if played right, it can help in that funding aspect of bringing forward the technology. We specifically went forward with the radiogels technology, that's what they termed it. And we were able to get enough funding so that the 2 MBA students could work on this for a period of time, and myself, and hit a few milestones. They always talk about milestones in the business school. Work with some initial FDA consultants, build the scientific advisory boards. These are things when we talk about valuation, as an engineer, it's not straightforward how it contributes until you really start to see the big picture. I think in terms of, well, you have to make sure it works. No, you also have to build a management team around it, and that's part of the training process that isn't necessarily obvious to most PhD engineering students. How the management team is so important. The end story to that is, we've continued to work on it, and most recently we get to learn one of the most interesting lessons that I think a lot of UW faculty have got to experience, and that's license negotiation. And in the end, we weren't able to reach a license agreement with PNNL on it, so it didn't work out. But the technology moves forward, continues to be incubated, and significant progress was made. And I think that that's a great example. Nobody would guess that technology transfer is such a difficult aspect, but talk to the professors like Dr. Kim or someone else who are dealing with it. Historically, it's very tough at the university. Recently, there's some new change coming out at the UW. There's hiring at the Office of Technology Transfer of Tony Claiborne, who comes from industry and who is actively working to try to facilitate this process better. And I think we're all kind of hopeful that that occurs. The last aspect, and I'm going to mention this briefly because this is obvious, of the clubs and organizations. What I wanted to do here was highlight you can become involved in these. You can go to the, every BESA, Bioengineering Student Associations, NSA, Nanotech, they all have industry relations. And, one of the things I wanted to do was kind of give advice here based on my own experience. And my experience was that it's one thing to go to these. It's another thing to really get involved in organizing them. If you're, the industry relations chair, the person, going out, reaching out to the community, I think that it is extremely beneficial for you to be in that role, then just go to it and get involved. I mentioned some of them. Seattle as well. They're great for networking, which people teach you is important for getting a future job. The last important slide here, and I put it for last for a reason, I have to emphasize this. Timing is critical. There's a lot of first-year PhD students in the room. Do not worry about this until later in your program. It won't benefit you. Number one, you need to get started on your research. You need to become experts. This requires, my first year all I did was classes and research. My second year, 12 hours a day, every day research. You need to become experts in this. The second reason is, once you are an expert in this, you're much more value to working with MBA teams evaluating technology than you were, let's say, your first year. And when you go out and meet people, you have a lot more knowledge and a lot more experience. And I think that you don't get that early on. And most of my involvement has been the last 2 years. And that's what I would recommend. There are a few other points. Communication with your advisor. That's critical. Lastly, a lot of people have been involved in kind of my education, and I'd like to highlight them involved with this aspect of it. Other than that, my contact information is below. Feel free to grab me.
Okay, thank you, David.